Okay, today we will be talking about how to calculate support reactions and handling support settlements in direct stiffness method. We can always calculate it by using hand calculations, drawing the free body diagrams, and from the free body diagrams we can go to the support reaction. That's fine. And we can always calculate the effect of support settlement as a Fixar moment. But here the question is, can we do it in the direct stiffness method? Or in other words, how can we handle these situations in a computer software? Okay, so in order to discuss that, I will use this simple example problem. So let's say that I have a structure like this. Let's not show the loadings here. Okay, that's the structure, and later on we will be analyzing this structure. But let's say that it's 20 meters here, 20 meters here. My aim here is directly obtain the support reactions, okay, without the need of going into the drawing the free body diagrams and using equilibrium equations and so on. Okay, so in order to do that, the first thing that I'm going to do is, again, we will do the discretization. So let me draw the discrete version of the structure, a node here and a node here. And let's determine the degrees of freedom. So this is my first degrees of freedom, D1, D2, D3, and D4. So in our classical solution, we say that the structure has 4 degrees of freedom. Now I will say 4 active degrees of freedom. So there is no supports in these degrees of freedoms, and they can move depending on the amount of loading we have. Okay, then as a second step, I will continue to number the degrees of freedoms. So in support I have D5. I know that it's equal to 0, but now I will continue to name it as if there is no support. Sorry, that's D6, that's D5. So D7, D8, and D9. Okay, and I got 5 passive degrees of freedoms. Okay, so since I have 3 nodes, I got 9 possible locations of degrees of freedom or displacement, but 5 of them are restrained by support conditions. So in that case, I'll have 4 active, these ones, and 5 passive degrees of freedom. And then let's say that we assemble the stiffness matrix. Okay, let's forget about the supports, and I assemble the stiffness matrix, a 9 by 9 stiffness matrix, okay, as if there is no supports. So we will have a stiffness matrix a 9 by 9 stiffness matrix. So I have some stiffness coefficients that belongs to the free or the active degrees of freedoms, and some stiffness coefficients that belongs to the restraint or the passive degrees of freedoms. So here let's put a note, these are free and these ones are restrained. Okay, and of course in this matrix we have these terms KFR and KRF terms, and if I multiply them, so for the first part I have the 3 degrees of freedom UF, and I have the restrained degrees of freedom, the degrees of freedom that belongs to the supports, right? So these are the degrees of freedom that belongs, or the displacement that belongs to these supports, and I know that they are equal to 0 if there are no support settlements. And that should be equal to, here I have the unbalanced forces at the nodes, and here I have the support reactions, or the forces at the restrained degrees of freedoms. So let's write their definitions. So UF is unknown degrees of freedoms, or the active degrees of freedoms, right? UR is vector of displacements at restrained or passive degrees of freedoms. It's usually 0, right? Because we have supports there, unless there's a support settlement. FF here is the vector of applied loading or unbalanced forces, and FR being the vector of support reactions. Okay, so if you think about it, until now we were only assembling this portion. We were using this portion of the stiffness matrix. We were not giving any degrees of freedoms to the supported displacements, right? Supported displacements as follows. So we were only generating the stiffness matrix of KFF. We have the unknown displacement vector, and this is the applied loading. So what I did different is I just first numbered the active degrees of freedom and then number the restraint degrees of freedom. So this way the stiffness matrix has the following form. So here the stiffness coefficients that we usually use, and these are the stiffness coefficients that belongs to these support conditions, and these two matrices represent the coupling in between. So let's do this. Now I have this partitioned matrix. Let's multiply this one with this one. That should give me f of f. This one multiplied by this should give me fr. So let's write it down. KFF multiplied by UF plus KFR multiplied by UR should give me the unbalanced force vector. And then my second equation is KRF multiplied by UF plus KRR multiplied by UR should give me the FR, in other words, the support reactions. Let's take a look at the case when all degrees of freedoms are restrained. Not all degrees of freedom, all degrees of freedom at the supports are equal to 0. This means that there is no support settlement. So according to our notation, UR is equal to all 0. There is no support settlement. So this means that these parts are all equal to 0. So our first equation becomes equal to KFF times UF is equal to FF, right? So this is the classical equation that we have been solving. K times U is equal to F, and this is used for calculating the unknown displacement. Now, once we obtain that, so from this equation we calculate UF. We obtain UF, and then we can use the second equation, KRF multiplied by UF will give us FR. This one is used for calculating the support reactions. So in that case, we are using the second equation to calculate FR, and FR will be our final support reactions. Now, when we have a support settlement, let's take a look at that. So in case of support settlement, in that case, UR is not equal to 0. So we have the following equation. So KFF times UF is equal to vector of unbalanced forces minus KFR multiplied by UR. So as you see, this expression here is actually the unbalanced forces due to support settlement. So with this approach, when I multiply the support settlements with the KFR matrix, I directly obtain the equivalent forces for these support settlements. And this expression gives a new force vector considering the support settlement. Okay, and again we solve this system of equation and we obtain what UF is, and then again we can use the second equation, which is equal to KRF times UF plus KRR times UR will give us the support reactions. So remember that this expression is support reactions due to displacements and this one is actually the fixed end moments due to support settlements. You can just think of it that way. Okay, so basically what we learned here is, if we do full assembly here, okay, first number the active degrees of freedom and then inactive one. Do the full assembly, you'll get a full stiffness matrix where you have all the coefficients that you need. Then partition it. So this part is the classical stiffness matrix that we use to calculate the unknown displacements. So use this equation. If you don't have any support reactions, support settlements, use this equation. If you do have support settlement, then it actually modifies your force vector, and use either this one or that one, obtain your UF. Once you obtain your unknown displacement vector, again, by using the second equation, this one, you can actually calculate the support reactions. Now we will solve two example problems to see how this approach works. Okay, now let's work on the example problem. So I will use the same structure. And I put some loading on it, 2 kilonewton per meter. I put a point load here, that's 20 kilonewton. It's applied from the middle, so that's 10 meters. This distance is 20 meters. And again, the height of the column is 20 meters. Okay. Now let's do the discretization. Let me give you EI value before that. EI is equal to 2 times 10 to the power 4 kilonewton meter square. EA is equal to 8 times 10 to the power 4 kilonewtons. So let's do the discretization. We did that before, but for completeness, I'll do it one more time. So I'm just first numbering the active degrees of freedoms. That's D1, D2, D3, and D4. And then I will show the inactive ones, the passive ones, D5. Sorry, this should be D6, that's D5, D7, D8, and D9. Now this is my first member, this is the second member, 1, 2, so that will be the local x prime, local y prime, local x prime, local y prime, and the rotation angle is, for this one, is as follows. That's theta, 270 degrees, and for the first one, theta is equal to 0. So let's first calculate the force vector. I don't have any support settlement in that case. The force vector that's my structure. That's equal to no deformation I have a point load here. Now the point load becomes a member load according to my discretization. and plus we have the only deformation case. And when you calculate the Fixar moments and forces, this one is 66.67 kilonewton meters. Again, 66.67 kilonewton meters, and I got 20 kilonewtons here, 20 kilonewtons. Now this one is 10 kilonewtons. This one is 10 kilonewtons. So I got 50 kilonewton meter as my moment, and this one is also equal to 50 kilonewton meters. Now transfer it to the node. I got 20 kilonewtons and 66.67 kilonewton meters. Here I got 10, downward direction 20, and this moment is 116.67, and I got 10 here and 50 kilonewton meters. So by looking at this, I will determine the force vector. Let's do that. So the force vector is equal to, this is the vector of unbalanced forces. I got the moment d1 there in the opposite direction, minus 66.67. d2 is equal to 10. d3 is equal to minus 20. And the force corresponding to d4 is 116.67. So that's the force vector. Now remember that when we do the calculations that we discussed for the support reaction, we actually calculate all the displacement, all the forces, support reactions due to deformations. Now I have to add the no deformation case also. So I should determine the fixed forces on the supports. So let's do that. Let me use a different color. So I should have the same force. I will not draw everything. Same force in the opposite direction at this support. And in the support, again, I have these forces. Okay, so here I'll not show the moment. At the end, it will be 0, 20 kilonewtons. And in the horizontal direction, there is nothing. And here I got 10 kilonewtons in the horizontal direction, and the moment, that is 50 kilonewton meters. Okay, so the Fixar moment fixed for the supports, I will show it with R, is equal to my first passive degrees of freedom is this one, and I don't have any force corresponding to it, so it's 0. My second passive degrees of freedom is this one, and I got 20 kilonewtons. They are in the same direction, so this is 20. Again, let's continue. Third passive degrees of freedom is d7. I got 10 in the opposite direction, so this is minus 10, 0, and plus 50. Okay, I'm doing the same approach. This is nothing different than recovering the member and forces. Remember that while recovering the member and forces, we calculate the member and forces due to deformations plus the fixed forces. We were doing it for a member. Now I will do the same thing for the supports. So these are the support reactions when there are no deformations. Okay. So let's continue. Now I will assemble the element structural stiffness matrix, and these are my matrices. This is the local element stiffness matrix, global for the first member, local rotation matrix, and the global stiffness matrix. Okay, so let's determine the mapping. So this is my first member. I will just show the local degrees of freedoms. That's D1, D2, D3, D4, D5, and D6. So when you do the transformation, you will obtain the forces in the global direction. So D1 is in global X, D2 is in global X, D3. So these are all the same. I'll just write it and pass it. D5 and D6. Let's take a look at the second member. So local, it's in the downward direction. That's the way we chose. So the local one is as follows. That's D1, D2, D3, D4, D5, and D6. Transform it global. D1 is in global X, D2 is global Y, D3, D4 is global X, D5 is global Y, and that's D6. So all I need to do is to compare this one with my global degrees of freedoms. So let me do this so that we can do mapping together. Let me redraw the structure here one more time. So my global degrees of freedoms, that's D1, D2, D3, D4, D5, D6, D7, D8, and D9. That's my first member, that's the second member. Okay, now let's map this with the global degrees of freedom. Okay, so 1 corresponds to 5 in the global, 2 corresponds to 6, 3 corresponds to 1. So let me write it down. This is 5, 6, and 1. 5, 6, and 1. Okay. Take a look at this one. 4 corresponds to 2, 5 corresponds to 3, 6 corresponds to 4. So I should write 2, 3, and 4, 2, 3, and 4. Basically, let's pick some numbers and see where they go in this global stiffness matrix. So this one will be assembled into K66, right? Let's choose this one will be assembled into K43, and so on. So this actually gives me the mapping between the local degrees of freedom, members degrees of freedom and the structures degrees of freedoms. Okay, so let's do the same thing for the second member. So 1, 2, 3 corresponds to 2, 3, and 4 in the structure. So I'm writing 2, 3 and 4 here, 2, 3 and 4. Again 4, 5, 6 corresponds to 7, 8 and 9. So I have 7, 8 and 9. Okay, so for example, this number will go to K29, or this number will go to K47. So you just take every number and place it in and add it in their locations in the structural stiffness matrix, and at the end of the day you will obtain a 9 by 9 global stiffness matrix. That's a 9 by 9 global stiffness matrix. Okay, so let's partition it. Let's divide it into pieces. So if you go back, as you see, I got 1, 2, 3, 4 active degrees of freedom. Let me correct this. This should be equal to 4. I just write 5. Let me erase it. So this should be D4. Sorry for that. So I got 4 active degrees of freedom. So let's go to the structural stiffness matrix. So 1, 2, 3, 4. So I will partition it from here. So this will be my KFF matrix. This is KFR matrix. This one is KRF matrix, and this one is KRR matrix. Okay, so KFF, and here we have the, let's call it FF vector. So I will use the KFF and this one to calculate the unknown displacements. So when I do that, this is what I obtain. So this is the solution. Okay, here I did KFF multiplied by UF is equal to FF. And by using that equation, I obtain the unknown displacements. Right? So once we have the unknown displacement, we will use the second equation, which is equal to KRF multiplied by UF should give me the support reactions, KR. But remember that this is the support reactions for only deformation case. Right? So I did that. This is KRF. Remember which matrix it is. That's the KRF matrix. So I'm using this matrix, this one, to calculate the support reactions. I multiply this matrix with the unknown displacement vector, which is equal to this UF, and obtain the FR. And remember that this FR is for only deformation case. In other words, this is the support reaction for this part, right? But I have these forces on the supports when there are no deformations, so I have to add this one to it. And this is what we do in the second step. So I'm adding that vector here, and these are my final support reactions. Write it in better way, final. So let's remember, this is our structure again. I have a uniformly distributed load here and a point load here. So my reactions are as follows. So this is in the global direction. This is 3.591 kilonewtons, and this force is 18.232 kilonewtons. So here I have force that's equal to 16.409. That's the horizontal force. The vertical force is 21.768 kilonewtons, and that's the moment in the counterclockwise direction, and magnitude is 92.818 kilonewtons. And these are the final support reactions.